Okay, so the original third speaker for this session, Santosh Kumar, I think he got caught up in the travel difficulties that have plagued this conference.
Yeah, he got caught up in what in the UK is called the hostile environment. So he didn't get a visa.
Okay, so our next speaker is David. I believe it's Ham, and so he's going to tell us about a complex value PDE support in UFL and Firedrake. Thank you, David.
Right. So this talk is an imposter because obviously it's not Santosh Kumar's talk at all. It has nothing to do with what's in the program, but it is a PDE applications talk because we don't normally think of ourselves as being an application. We think of ourselves as being a framework that has users who do applications, but actually applied is a relative term. So in this room, we're an application. And I'm going to, for those of you in the room who don't know what Firedrake is, I will briefly sketch a little bit about how Firedrake works in a second so the rest of the talk actually makes sense. But ever since we started the Firedrake project, about once every 2 months, someone will pop up on the list and say, can I has complex, please? And because there are obviously important classes of application where the PDEs are stated in a complex space, and the standard hack of decomposing your PDE into a real and a complex part plays merry hell with every single layer of the structure you're playing with. You didn't want to do that. It turns out that you can have freefen++. freefen++ supports specifying stuff over the complex field, and so if that could do what you wanted, then that's fine, but that doesn't get you all of the joys of PDE and everything that Firedrake can do for you. And so I had a wonderful master's student, Nick Barton, who is now in Oxford, who did this for us. And in fact, those of you who know about FEniCS are now lifting this code into FEniCS. They've got a Google Summer of Code student to lift this stuff in there. So as a consequence of this, you will, by the end of the summer, also have complex FEniCS. So what is this game we're playing at? So there is some sort of law that says that when you explain how one of these PDE, how one of these finite element method frameworks works, what you do is you write up the Helmholtz equation. I apologize to anyone in the room who wanted me to solve the hard Helmholtz equation. We normally do fluids, so we get to do the easy one, which is the one that's up there. And what do I do when I want to solve this using the finite element method? Well, the first thing I already did, which is I write the Whig form of the equation for every test function in some space V. And then I write out the code that solves it. And the operant thing here is that there is the equation, and there is the code writing that equation. So the gradient of the test function inner product with the trial function minus v times u times dx, and there is the right-hand side. So the times dx is the integral because ASCII does not have an integral sign. Unicode almost certainly does, but like hell lies down that particular route. And so what I've got here is effectively Mathematica or Maple. It is a symbolic representation of the problem. And then what happens is you say solve the problem. And when you say solve the problem, what happens is a compiler, a specialist compiler that reads this language, sucks this in and writes the C code that would assemble the operators, compiles it at runtime, and jumps into the C code to assemble the matrix on the right-hand side, or if it's a nonlinear problem, hands those callbacks over to SNES like Matt explained yesterday, and then we let PDE solve the system, we get an answer back. So basically, you write down the equation, magic happens, you get a solution. If you MPI run this script, it does exactly what you would expect, and you get the answer in parallel. So the core concept, so the core thing this delivers is a spectacular change in programmer productivity. And for most use cases, programmer time is the most expensive thing in the system. It is also fast because those compilers do optimizations that are far too horrific to do by hand. So for example, when you've got your finite element loop nest, the compiler solves a discrete optimization problem for the correct loop ordering and which temporaries to remove and take up the stack. So you could do that by hand, you probably wouldn't. And so it also is a performance enhancer. It also means that we can symbolically reason about these guys. So we can do symbolic maps on the operators before we solve them. So there is a thing out there called Dolphin Adjoint that Patrick Farrell, Simon Funke, Marie Rognes, and I wrote, which enables you, given a problem written like this, to automatically solve the adjoint. Also time varying, also doing no checkpointing, all that sort of stuff, because you can symbolically reason about the problems. Patrick Farrell has a deflated continuation solver that automatically reasons about these problems. Lawrence is going to talk about how you can use the fact that you have the operators here to do better preconditioners later on. And in fact, Thomas, in another talk, is going to talk about other ways that you can symbolically reason about this to change the linear algebra problem that you have to solve in order to get a better system to solve. So,
just to note that is, in fact, the bad cop helpers.
oh, is it?
It could be worse. It could be worse.
Fine. It's traditional to make sign errors. Okay, but that's all other people's talks. This is a talk that about this question of, so how can I have complex? So what actually goes on under the hood is you saw that layer, which is a symbolic layer written in Python, and we just call out to PDE for Pi. Thank you, Alessandro, it is amazing. And so that gives us all of our solvers. It also gives us the parallel data structures, because we use dmplex. We sometimes cheat a little bit in how we use dmplex, but we add it to the core, we use dmplex. So this bit is PDE as you know it, but PDE per se doesn't have anything to say about where the operators came from. And so this part here, this is the form compiler. So the form compiler needs to do two things. It needs to be able to translate symbolic expressions into C. Well, that's kind of straightforward because most things you can write down at the top also exist at the bottom. It also needs to know how to do the calculus bits. So it needs to know how to represent test functions and trial functions and whatever else. So it turns out that about, oh gosh, pushing on for 20 years ago, Rob Kirby came up with this thing called Fiat, the finite element automatic tabulator. And so this thing uses Chiale's abstraction for a finite element to give you a ridiculously large zoo of finite elements that you can tabulate. You can call, you can say, I want the fourth order Nadelic element on a tetrahedron tabulated at this set of quadrature points. And so that thing out there gives you the calculus smarts that you needed. These days, we have something I'm not going to talk about here, which is a much higher symbolic layer called finite. And finite gives you not just tabulations, but actually the symbolic expressions, which means that if you're on a quadrilateral and you have a tensor product decomposition that you could use to do some factorization, this thing will give you the tensor product decomposition, and then this thing can do its optimization tricks, which will automatically sum factorize the operator. So you get the optimal complexity assembly algorithms. And so that does all that. And then you get down to a layer which is just doing software engineering. And it is generating for you the loop over all the cells, it compiles that, it calls that, it glues all the things together for you so you don't have to care. So, what was it we wanted to do? Oh yeah, we wanted to change the class of problems we solve. So basically, the class of problems that we solve are things that look like this. So that's a weak form in the most generic sense. So find this guy with parameterized by a whole load of things tested against this guy. That's what the whole world looks like. The only thing that's changing is hitherto these guys are all real, now they're complex. The domain is still real, so it doesn't necessarily have to be, but I haven't thought through all of the nasty implications. And in fact, the coordinate field ends up in the complexes, so it's entirely possible that you can feed complex values in and something sensible will come out, but we haven't tested it, and I'm not making you any promises. So that's the problem we wanted to solve. And how do we do this? So the first thing we're going to do, we're going to have to like trawl through this whole graph that I just showed you and turn everything complex. Fortunately, life is not as bad as that. So the first thing we realize is complex finite element spaces aren't as bad as you think. And the reason they're not as bad as you think is that a finite element space is, by definition, a function space. So in particular, that means that if you multiply something in the function space by a scalar, you stay in the function space. The scalars are now complex. So that in particular means you can multiply by I. So you can rotate things around and they stay in the space. That basically tells you that your basis functions are real, or at least that a real basis exists. So therefore, you can ignore all of the complex stuff when you're dealing with all the stuff Rob deals with. So that part of the thing stays real, and we just put complex coefficients outside, and we can still deal with every case that we actually, every case that's legal. Not even just every case we care about, every case that's legal. So phew, we're off the hook there. Okay, we've got to be a bit more careful about what we mean by a linear or bilinear form now, because they're not the same in complex land. So when I wrote that, I didn't really mean that. That's what everybody writes, but actually it's always an inner product with the test function. An appropriate inner product, maybe an H1 or some other weird sublot space inner product, but it's always an inner product. And that now matters because in real space, inner products are bilinear. And so that's very, very easy to deal with. In complex space, inner products are not bilinear, they are sesquilinear because they take the conjugate of one of their arguments. So now all of a sudden it really, really matters where in this system you're taking inner products. And so we're going to have to think about that to make the UFL layer come out legally and not just silently produce rubbish, which is quite easy to do in this case. We also then have to assemble down to a linear algebra backend, and the linear algebra backend is now going to have to do everything in complex as well. Now, fortunately, the people who wrote PDE aren't idiots, so PDE's complex support does the right things in the ways that you would think. So when you matrix vector multiply, it does the thing on the tin, and when you dot product, it takes the conjugate of the appropriate argument. So as long as we do things the right way round, we end up there. So now we run into our first little hiccup, which is the community does not agree on which way round the right way is. So depending basically on whether you are a pure mathematician or a physicist, you take the conjugate of either the first argument or the second argument of an inner product. The one that matches what PDE does best is to take the conjugate of the second argument. So we're going to take the conjugate of our second argument, which translated into finite element space means that we put our test functions on the right-hand side of our inner products. I'm sorry if you come from one of the bits of maths where that's the wrong way round. You have to make a decision at some point. If you don't make that decision, you have to multiply out a combinatoric explosion of all the symbolic things that are now legal in UFL space, and that's just bad. So we're not doing that. So what do we need to change? So the basic Firedrake FEniCS language is fine by itself except for UFL. So a function space is still a function space, a mesh is still a mesh, a function in a finite element function space is still one of those things, solve still does what it says on the tin. That stuff's great, so we don't have to touch that one. PDE is fine because it does complex. It does complex in a particular way that will affect a choice we're about to make, but it does it. This one doesn't have to care. The compiler and these layers, it's a simple matter of debugging. So these guys are parameterized by scalar type anyway. And they are, because this is all runtime code generation, they are much more parameterized than PDE. So PDE has a scalar type. Every single operation, every operand has a scalar type that can change. So that's just a question of debugging, and I have a great master student. So that's mostly good. So actually it comes down to what do you do to the symbolic finite element language to make it complex safe. And so what do you do? Well, you've got some options. So you could type everything in UFL. At the moment, when you say finite element function, you didn't actually say what the type was, it's implicit. So you could type everything in there. That is the most general solution, but it's massively invasive, and it would require a whole load of boilerplate for users who didn't care about complex. So that's done. We're not going to go there. It's also too much work. Also, it's not really compatible with PDE, because I can make symbolic expressions that have got mix-ups of real and complex as much as I like. As soon as I pass it to PDE, PDE's only got one type. So I'm either compiled in real mode or I'm compiled in complex mode. So we jumped that one. We could have introduced a global scalar type for UFL. I use the word global, you know I'm already wrong. Basically, that would have, particularly because UFL is totally dynamic, introducing a global into a dynamic language particularly when it's Python, you can't stop people from changing the global later. It's like everything is going to go wrong. So that's wrong. What we do is we actually extend UFL so that the symbolic layer doesn't need to know whether we're real or complex. So we go, everything is complex in principle in UFL. And what happens is we deal with real as a special case, and we do the right things if the underlying layers, if the compiler knows that the underlying layers are real. We can come into that in a second. So, first bit's easy. You put the additional things that only exist in complex in. You have to be able to take the conjugate. It turns out that depending on whether you look at core Python or NumPy, conj is spelt either conj or conjugate in Python. So thanks, Python. So we support both. And we have real and image. That's fine. That bit's easy. UFL does canonicalization of order of products. So UFL turns A.B into B.A if in its arbitrary symbolic ordering they're in the wrong order. That's a good thing because it means symbolic cancellation happens a lot more effectively. But you do have to go through and make sure that that's now complex legal. So it will introduce conjugates. And it will do that even in the real case. That's fine, right? Because the conjugate of a real number, it doesn't do anything. And conjreal and image causes a little bit of a problem. Complex analysis is horrible. In the complex space, nothing is differentiable. Okay, that's not quite true, but like lots and lots of things that look like really, really inoffensive functions turn out not to be either linear or differentiable, such as any of these guys. Conjreal and image are not linear, they're not differentiable anywhere, they suck. But that one, these two are no ops on the real field, and that one is the zero function on the real field. So we need to do something about that. So what we actually do is we lie, and we say, these guys are actually linear functionals, so they'll go through all the automatic differentiation just fine, and we'll mop it up later in the complex case. We'll chuck an error later down the stack, because otherwise we break the real case, and if we break the real case, no one's ever going to use Firedrake again. Small diversion into what that form compiler actually does. So right at the top, it's doing a whole load of finite element type stuff, like computing the derivatives, putting the change of coordinates between the reference space and the physical space, working out what quadrature it needs if you didn't tell it, and most users don't tell it, they just rely on us to get full quadrature for them. Doing all those sorts of things. All of that stuff is fine. And right at the end, we check form-arity. So checking form-arity is us making sure that your form really was a form. So it has a test function and a trial function in every term, or just a test function every term, or no arguments if it's a zero form, that's legal. But they all match. And you didn't do anything nonlinear to a test function or a trial function, because doing a nonlinear operation to a test function or a trial function results in something that makes no mathematical sense. It's not a form. And the form compiler will die with an appropriate error message if you do that. This is good, because fast user feedback rather than just producing junk code, producing the wrong answer. So what do we do? Well, I told you we need to be able to handle the real case, and so the compiler, so UFL doesn't have a real or complex mode. Everything is in principle complex. But the compiler is compiling for an actual backend, i.e. us or FEniCS. And so the compiler at compile time knows whether we're in real or complex mode. So if we're in real mode, it just drops all the complex nodes on the floor. And if we're in complex mode, what it does is it augments the linearity check to make sure that you are linear in the trial function and conjugate linear in the test function. So then that drops out for you, which means that the users now have to be more careful, but they only have to be more careful in the case where it matters. So it will correctly deal with all these cases. So that's illegal because that's a nonlinear function. That's always illegal. That's right, and that's wrong, because the test function has to go on the right-hand side of an inner product. And that will get triggered because when you lower this, this will have a conjugate on it, and we'll notice, and we're going to do it. That is what everybody writes, and it's kind of right unless you're in complex, in which case it's completely wrong. So that will die in the complex case and not in the real case. That's all right. So it's doing all the simplifications correctly. So you don't have to have written stuff in a particular form. You just have to have written something that is mathematically right. We will lower all the form you wrote out, and we will check that you got it right. And so similarly, you can do this. You didn't actually have to write an inner product. You can write out the lowered form if that's what floats your boat. We also had to screw around a little bit because people write upwind schemes. People write other things that have comparison operators on them, and there are no comparison operators on the complex space. But remember, right back at the beginning, we decided we weren't going to have reals and complexes in here. So what we do is we symbolically prove whether or not the arguments to a comparison operator are in fact real. And if they're in fact real, that's fine, and we explicitly wrap them in a real, and then they'll go through the compiler and it will work. And if they're not, we die. So that's actually very, very hard, because generically proving whether or not an expression is real or complex is Turing complete operation, so we're screwed. But you can get the common cases, and you just defensively die in the other ones, because the user can always explicitly wrap their expression in real. And if they explicitly wrap the expression in real, then it's good. So that's not a problem. So last thing we do is a very simple example. Rob and his student have been using this, which is brave, because it's probably still buggy. No, it's not probably still buggy. It's definitely still buggy. But they have more exciting things. But this is the boring one. So this is us solving Helmholtz again. This time, I really have done the easy one. So all I'm doing is forcing it with a complex value. In Python, unfortunately, the electrical engineers got at the syntax people, so the complex thing is J, not I. It's a bit sad. And the proof of life is it does what it's supposed to. P2 is superconversion because it's on a structured mesh and there's a symmetry. It's not a big surprise. So what I told you is we've done the legwork to symbolically extend the symbolic language. That is the thing that drives both Firedrake and FEniCS, actually, to give you complex. And we've done the grunt work underneath such that you get, in most cases, legal operators, and PDE does the rest, obviously. So that's all I'm going to say, and just to flag that I'm still smashing the paperwork through the bureaucracy, but we are in the process of hiring a postdoc to be a Firedrake core developer, so if you know somebody who is in the market for that, I want to talk to them. Also, you will have noticed that the key and critical failing in the entire PDE project is their lack of adequate branding. This is not a problem that Firedrake suffers from, and you will have seen all the people with the stylish Firedrake stickers on their laptops. If you feel that your laptop is sadly lacking in a Firedrake sticker, they're down the front here. Thank you very much.
Questions?
Yeah.
The complex numbers do admit a well ordered because of the axiom choice.
Fine. That is a pedantic point. Doesn't change anything about what we needed to do. It still means that A less than B is only a legal thing to do if we can prove it's real, right? That's the only thing that matters. And also, like, you know that. It's the only thing that makes sense, right? Those switches are in there to check things that can only possibly be real. It's not. It's just that you give users a symbolic language and they will write down any old crap. And so you have to correctly handle any old crap, even if the correct thing to do is bath. But you do need to then actually bath. Cool, okay, so I should stop talking here about this. I'll stop the recording and let you know what's happening next.